All right then, time is 8 p.m. GMT, and a very warm welcome to the second event of the webinar series dedicated to vector symbolic architectures and hyperdimensional computing. My name is Evgeny Osipov. I'm from Luleå University of Technology in Sweden, and I will be moderating this webinar. So I'm very glad to see new people joining this webinar. Today we have two exciting talks. As previously, so please use chat function to write your questions. We take all questions after the end of each talk. I also want to remind you that the webinars are recorded so that we can make them available offline on the website, but I will send a separate email with the links. All right, so today, as I said, we have two talks, one by Denis Kleyko and another one by Stefan Reimann. So Denis, you can start sharing your screen, and while I'm introducing the topic of your talk. So Denis' talk will be about vector symbolic architectures and density encoding as enablers for resource-efficient, randomly connected neural networks. So without any further delay, so I leave the floor to Denis. So Denis, please, and I mute myself.
Thank you for the introduction, Evgeny. So Evgeny already said the title of the talk, so we can safely skip the first slide. And I'm going to talk today about randomly connected neural networks. And randomly connected neural networks is a family of, or one can say is a class of several types of neural networks. So when we say randomly connected neural networks, we usually talk about feed-forward networks, recurrent networks, or about randomized kernels. And the main idea is that we have two fundamental ideas when we use randomness. So the first idea that we use random values in order to define the feature map, which transforms our input in a high dimensional space. And the second fundamental idea that when we do so, the resulting optimization problem it can be cast as a standard linear least squares problem. And that's is an advantage because then we don't have to use iterative optimization methods. So we can just simply use the standard regression in order to get the rest of the weights of the network. So when we look at the feed-forward and recurrent neural networks, we have pretty similar architectures, with the only difference that recurrent neural networks, they also have the recurrent connection in the hidden layer, while in the feed-forward network, as the name suggests, there are no recurrent connections. And recurrent networks are usually known under the names of echo state networks and liquid state machines, while the feed-forward neural networks, they're usually known as random vector functional link networks, or RVFL. I will use this acronym in the rest of my talk. Or another popular term is also extreme learning machines, or ELM. So when we look under the hood of the feed-forward neural network, what will we see? We will see that the network has three layers. It has input layer, which is denoted as X here. Then it has the hidden layer, and it has the output layer. And the connections between the input layer and the hidden layer, they are fixed and random. So we don't change these connections during the training process. And they're denoted here as WIN. So which means that we already once we initialize the network, we can obtain the activations of the hidden layer, and the activations are obtained as multiplying the values of the input layer X by W in. We add the bias vector, and we also apply a non-linearity function, which is TNH, or it can be a sigmoid function, for example. And the trainable part of the connection in the RVFL is between the hidden layer and the output layer. And this is denoted as W out. And this is the part which is obtained using the regression. Usually it's a rich regression. So we have also lambda parameter, which defines the regularization component of the linear regression process. And then the output of the network, once we obtain the W out, would be just, sorry, here we have a typo. So it should be multiplying W out by H. And it would provide us the output of the network. Now, just in order to represent the conceptual idea of the proposal, I just want to mention that when we think about this part, projecting input layer into the high dimensional hidden layer, we can think of it as if every neuron would be a sine wave. Let's just think about it for a while. So every neuron is a sine wave. And then we have the input feature, or the value of the input feature. And then the feature has the corresponding sine wave. And then the value of the feature would scale the amplitude of this sine wave. And it happens for every feature. In this tiny example, we have 3 different features. So, and then once we project all our sine wave by the corresponding feature value, so we get several sine waves with the varied amplitudes. So we have the red lines, or the red dashed lines here. And the part of combining these values in the hidden layer is depicted here. It's a superposition. So we superimpose the red curves in order to get the total activation caused by 3 features. That's what is done conceptually in the standard RVFL. And what we propose to do instead is to use scaling by density instead of scaling by amplitude. And in this example of sine waves, we can think of scaling by density as of actually swapping the phase of the sine wave at the fraction which corresponds to the proportion of the feature value. What I mean here is that we assume that the maximal value of feature is 1. And then if the actual value is 0.6, it means that we have to swap the sine function once like 60% of the sine function has passed. And here we also assume that the duration of the sine function is also fixed. So in the second feature, we have 0.3. So of course, we swap the sinusoidal function for much shorter time. And then we have 0.7. So this is the longest duration. And then once again, we superimpose the sine waves together, and we apply a nonlinearity, let's say TNH. And the red curve then would be our activation in the case when we do scaling by density instead of scaling by amplitude. And this is the main conceptual idea of this topic. But now we go into practical details. Like, of course, we're not going to work with a sine wave. we're going to work still with numerical vectors. So how do we do it when we work with numerical vectors? And for that, we will use a technique which is called density-based encoding. So the idea of the density-based encoding is that we can actually take the scalar value and we can project a scalar value into a vector. And as the name suggests, the density-based encoding is that the density of active elements in the vector would actually indicate the scalar value. Here we have an example. And in the example, we see that we have in total 4 neurons. And then when we represent the value which is 0, all neurons are inactive. We can think of it of these neurons all being set to 1. And then when we have when we make the representation of the next level, we activate only 1 neuron. And we can think of it as being equal to -1. So we have the first neuron is -1, the rest are +1. And we continue in this manner till we reach n, where n is the total number of neurons in the vector. And in this case, n is equal 4, so which means that in total we can represent n+1 or 5 different levels. That's the density-based encoding in essence. And we will use the density-based encoding, or it's also known as a thermometer code. So we will use this thermometer code in our modified version of RVFL in order to represent the values of features in the input layer. So when we look at the modified version of the architecture, we see that we introduce a new layer, which we call density-based representation layer. And we see so that the connection in this layer, they're highly structured. So we have one vector in this layer corresponds to a particular feature. And why we call these connections feature dependent, that is because the actual value of feature in the input layer would determine which of the neurons will be active in the density-based layer according to the thermometer encoding. And then the rest of architecture stays the same, except that now the connections from the hidden layer, before all of the connections, or before there were several connections outcoming from a single input layer. But now once we introduce a density-based representation layer, we only have a single connection from a single neuron in the density representation layer. And we will see at the next slide how to actually interpret this in terms of vector symbolic architectures. So when we start to think about this modified version of RVFL in terms of VSAs, we can say that actually the weight matrix, the WE matrix, it will be random and bipolar, and then actually this matrix can be interpreted as a set of HD vectors, one vector per feature. So in other words, we can say that we actually assign a role vector for every feature. So we assign a role HD vector for every feature. And then since every feature now also produce a thermometer code, we can apply the binding operation in order to make the association between the current value of the feature, which is represented as a thermometer code, and a particular role vector of that feature, which is just random bipolar vector. So the binding operation will provide us a set of key value pairs. So one key value pair for every feature. And then the next step would be to apply the bundling operation. So we make a superposition of all key value pairs. And this operation would correspond to the linear activation of a hidden layer. And the next step in the hidden layer would be to apply the nonlinearity. And of course, we can still use the TNH function, but instead we will use another activation function, which is called clipping function. So we can see the clipping function here. So the clipping function, what it does, it keeps within certain range, which is determined by the parameter called kappa. It will keep the values just being linear, and then if the value is outside of that range, it would be equal either kappa or minus kappa. And these are all the steps we do in order to get the modified version of RVFL. So let's consider a numerical example. In this example, we just take a particular network, assuming that it has only 5 features. And we also assume that the size of the hidden layer, or the number of neurons in the hidden layer, only equals 10. So what are the steps we have to do in order to get the activations of the hidden layer according to this new modified RVFL version? So we have to take our input features, and we say that the input features, they should be in the range between 0 and 1. So they should be normalized to be within that range. Then we have to quantize the value of every feature. That's because this thermometer code, it has only n+1 levels. So we can only represent n+1 different scalars with the thermometer code. In our case, n equals 10. So we quantize each feature value accordingly. The next step would be to produce the thermometer code, or in other words, we activate this density-based representation layer. And you see that what we simply do here is that we take the quantized value of the feature, and this value indicates how many of the first positions would be equal to -1, and the rest would be equal to +1. So we see that, for example, feature 3, all the values of feature 3, they're being equal to -1s. And for example, for feature 5, we have only one value, the first one, which is -1, and the rest are +1s. Then we have our W-in matrix, or a collection of role HD vectors. And once we have both the role HD vectors and the activations of the features in terms of thermometer code, we can do the binding operation. And the binding operation, the result is represented here. And as we actually can see, that what happens is the binding, in the case of bipolar vectors, the binding is simply a Hadamard product. So what happens is that what we simply need to do in order to do the binding, we simply need to inverse the sign of the first of several first components in the corresponding HD vector. Like in the case of first feature, since the quantized value of that feature was 3, we have to inverse the first 3 signs of the HD vector, and the rest stays the same. Then once we do it, so we can calculate the superposition of these vectors, and the superposition is represented in this vector. So this is a linear activation of our hidden layer. And the final step would be to apply the nonlinearity with a clipping function. And in this example, we choose a clipping to be 2, which means that, for example, the first position is being equal to -3. So when we apply the clipping function, so the value would be changed to -2, just because -3 is more than -2. So we have to clip this value. The values which are within the range of the kappa, they will stay the same. So now, of course, once we have this modified architecture, the question is, how would it perform in comparison to the conventional RVFL? And for that, we perform the evaluation using 120 different data sets, which were studied before in a large-scale study, studying just different classifiers. And here you can see the characteristics of the data sets. And the only pre-processing step we've done was to normalize the values of the features to be between 0 and 1 so that we can use the thermometer code representation. And just to provide some additional context, so the best classifier, which was random forest, so the accuracy of the best classifier was 0.82. And the average accuracy among all data sets for just the linear classifier was 0.73. So on this slide, we see the results in the case what we call unlimited resources. It means that we just perform the hyperparameter optimization using the grid search in a large range of the number of hidden neurons between 50 and 1,500. And then we calculated the cross-validation accuracy for both the conventional RVFL, which is x-axis in the figure, and for the proposed approach, which is y-axis. And every point in this figure is the accuracy of the data set, which means that if both approaches, if they would perform absolutely the same, then all the points would lie on the diagonal, which would mean that both approaches would get exactly the same accuracy for each data set. But we actually see a different picture. We see that the proposed approach, on average, or on many of the data sets, it performs better. And as a result, the average accuracy of the proposed approach is actually higher than that of the conventional RVFL. And here we actually can see the numbers. So the proposed approach was 0.8, and the average accuracy of the conventional RVFL was 0.76. And we also performed some extra experiments just to guarantee that indeed, if we play around with different modifications of the settings of the experiment, we get the same results. And then the next step, which we've done, was that to quantize the value of the readout. And by the readout, I mean the connections which are trained using the regression from the hidden layer to the output layer. And of course, since we use the regression, by default, we would get real valued entries in this matrix. But since we're interested in trying to implement this algorithm on FPGA, we want to get rid of the real valued data. And of course, by the design, up to the activation of the hidden layer, we only work with integers right now. And so the only step where we would have to use the real value data is readout, and we want to get rid of it. And for that, we consider three different strategies. One would be simply taking the readout obtained by the regression and quantizing it into a given range. And this is a red dashed line in the figure. And it's plotted against the increased range of the allowed integers. And we see, of course, and the larger is the range, the better approximation we would get. And the black line is the actual accuracy with the floating point, or with the real value readout. And two alternative approaches were also to use the genetic algorithm, which is either initialized by the quantized readout, or the genetic algorithm which is initialized randomly. And here we can see that actually when the integer range is very small, then the initialization with the genetic algorithm actually improves over the quantized readout. And the genetic algorithm which is initialized randomly also performs better. But when we keep increasing the integer range, it seemed that the best thing to do would be just to simply quantize the readout, which is obtained by regression. And now, the last point here is that now we have fully integer version of the algorithm. And once we implement it on FPGA and compare it to the implementation of the conventional RVFL for a particular size of the network, we would get 11 times of improvements in energy, and it was 2.5 times faster. And an additional experiment which we performed is using the limit resources, what we've called, and it's in a way one can think of it as being a simple way of getting the bounded optimality. When we have a limited amount of resources, in this case it's energy, and we want to see how different algorithms would perform in this case of limited resources. And effectively, in case of RVFL, the limited energy would limit the size of the hidden layer. And of course, we set it on purpose to be less than the optimal values, which we had in the unlimited case. And also the comparison was done with a finite precision RVFL, just to be more fair. So the finite precision RVFL works with 8 bits. So we don't implement full scale for floating point operations. And we've seen that the fixed point RVFL, the average accuracy was only 0.65, while the average accuracy of the proposed approach was 0.73. And I think I'm getting out of time, so I have a few more slides, but we will conclude here. So the takeaway is that we now can do randomly connected neural networks, but which are formalized in terms of vector symbolic architectures. And in this work, we were using the framework of VSA, which is called multiply add permute, which is very similar to binary sputter codes. But of course, now we can use any other framework. For example, we can use frequency holographic reduced representations. And that can allow us implementing these algorithms on different hardware. For example, it was recently shown that the map framework can be implemented on using memristors, and there might be ways of implementing the frequency holographic reduced representation using spikes. And this is a venue for the further work. And just to pitch a little bit on that, I just want to say that we made one step further, and then we did the same experiments using the block sparse VSAs, which is, so you can read actually more about them in this paper. But the idea that our HD vectors are very sparse and they have block structure now. And we also proposed a special modification of the thermometer code using block sparse code. And then we performed the same experiments using the block sparse VSAs. And we found that the average accuracy was preserved. But as an advantage, we now get the sparsity as well in the activations of the hidden layer. And that was last slide in my presentation.
All right, thank you. Thank you very much, Denis. So we have at least one question in the chat, unless somebody wants to contribute with more questions. Okay, we have a couple of questions in the chat. I don't know, do you see the chat so that
no, I can't see the chat right now.
Okay. So the first question is from Ross. Was there a comparison of network performance versus linear regression from the inputs?
Yeah, exactly. So this is a result. This is a result here. So by the linear classifier, I meant the linear regression from the input. So the average was 0.73, which means that RVFL improves over this result, and the proposed approach also improves over this result.
Okay, so we have another question from Pierre. Can you say something about the relative sizes of the RVFL and the proposed approach for the same task?
I got the question. So I think, yeah, if from the top of my head, I think the proposed approach was let's say about 15% more neurons on average. So in this case, when we work in the case of unlimited resources. So we've got coarser neurons in a way that they were now only working in an integer range. But the optimal values after the grid search, they were slightly larger. But surprisingly, when we check the last slide, if we check it, so we see that when we're using block sparse VSAs, surprisingly, so the block sparse dimensionality, the average dimensionality was only 500 against the 750 in the case of dense representations. And that was pretty surprising because intuitively we were thinking that if we use sparser HZ vectors, it might be reasonable that these sparse vectors, they would require more dimensions to get similar results. But it wasn't the case.
All right, so there was a second part in the question. Is the lower power consumption also due to the fact that the proposed approach is has fewer neurons?
No. In this case, it was due to mainly due to the fact that in the proposed approach, all the neurons they operate with integers only, so we don't have to implement the floating point operations. That was the main source.
Yeah.
Because essentially, if we look at this part, this is actually the activation of the hidden layer. So we have only plus and minus ones as a roll vector, storing the roll vectors in WIN matrix. We have only plus and minus ones as the activations which come from the features. So the bound representations, they're also only plus and minus ones. And then the activation of the hidden layer, these are integers within a fixed range. And this range, it wasn't large. I think we ended up using values of kappa which were either 1, 3, 5, or 7. So which means that when we use kappa being set to 7, 4 bits is enough to represent a single neuron.